This is the solution video for problem set 9, problem 4, and this is part 1, where basically I want to translate 3 LC3 instructions into their instruction codes. So I've copied the information from the handouts that we give you just to make life a little bit easier so you can see everything at once. And to start, we want to translate the instruction AND R3 with R6 store into R1. So this is our destination register. This is SR1, and this is SR2. So our instruction word is 0101. DR is going to be R1, so that's going to be 001. SR1 is 3, so 011. This needs to be 0, this will be 00, and SR2 is 110. That's pretty straightforward. Now our next one is LDI. R2 is our destination, and our offset is going to be -16. Well, -16 is pretty easy. We just need to set bit 5 and everything above it to negative to 1. So -16 is, at least to start, is 10000. So this is -16 and 2's complement if we have 5 bits. And then so we just need to extend it to 7, 8, 9, 6, 7, 8, 9. And then our destination register is R2, so that'll be 010. And LDI is 1010. Next up is branch. So BRNZ, sorry, this should just be BR. Now we're going to do BRNZ and 5. So here, N we're going to need to set to 1, Z we're going to need to set to 1, and the number 5, we're going to assign extend that up to 9. So 0000, N needs to be 1, Z needs to be 1, P is 0, and then the number 5, so we're going to have 101, so 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros to complete the instruction word. So that completes part 1, and moving on we will need to grab a new sheet of paper and start doing part 2. So part 2 is where we need to write a program where we want to solve for part 2. We need to write a program where we have A XOR R2 R5 into R4. Now, I actually haven't solved these problems yet before, so hopefully I can do this on the fly and do okay. So I need to implement XOR. And all I have in my architecture are AND, ADD, and NOT. Well, hopefully you remember this from earlier in the course that we can express any function with just ANDs, or NANDs, and NOTs, pretty much. So basically, I'm going to start off with, originally I have, let's suppose I'm doing A XOR B. Well, that's just going to be equal to A B bar or A bar B. If I do involution, I double complement this, I should be able to make it all into just NANDs. And so this should can be A B bar complement, and with A bar B complement, and then we will have all of that NAND together. So I'm going to need to keep R5. Let's make this R5, this R4, and we're going to stick this into, well, I'll stick this into R2 to begin with, maybe, and we'll stick this into R3. And then we can, after we do this, so we're going to need to keep track of all those, and then we'll AND these two together and stick that back into R2, and then we'll AND these two together, stick that back into R3, we'll NOT them, do the same thing, and then AND R2 and R3 together, store that into R2 and not R2. So instruction, so let's pretend I have a program counter, and it's going to start at 0, 0, 0, 0. Hopefully it won't take too many more than that. And so for my first instruction, I want to not R5 and store into R3. So I'm going to take not of, so this is going to be R5, comma R5, and, oh, no, sorry, not R5, I want to store that into R3. And then I'm going to not, so this is program counter 001, R, so I'm going to store R2 with the not of R4. And then I'm going to move my next program counter up. I want to AND these A and B complement, so it's going to be R5 and R2 together and store that back into R2. So we're going to AND R5, comma R2 and store that back into R2. And then we will not R2 and store it back into itself. So now we've got that. This has been ANDed, and now they've been NOTted. And then we've got, for the next one, 0, 1, 0, 0, we're going to AND R3 with R4 and store that back into R3. And so that's now the AND. And now we want to go to the next PC. So this is going to be not R3 back into R3. And so now we've got R3 is this whole thing and R2 is this whole thing. So we're going to AND R2 and R3 together. So for instruction 6, we're going to AND R3 with R2. We're going to want to store that into R2. And then for instruction 7, we're going to not R2 and put it back into R2. And that will complete part A. Now for part B, we want to implement logical shift left R3. Well, hopefully you remember this from what I've mentioned earlier in the class, that pretty much a logical shift left, or any kind of shift left, basically except for circular, is basically multiplying by 2. And so multiplying by 2 is the same thing as adding with yourself. So if I make my program counter, let's just make this 8 to keep going. This will be, so for logical shift left, it's exactly the same thing as adding R3 with itself and storing back into R3. And so I can do an example of that on the side, but basically this program is add R3 with R3 and store into R3. So just a quick example. My register was originally 0110, just for a 4-bit example. And I want to shift this to become 1100. If I just add 0110, I get 0 plus 0 is 0. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1, 1. It's the same thing.